Alright, hell yeah. So we have part 2. Now we have a pretty complicated dynamics problem. At some point we're going to do some differential equations. Part 2 is just going to kind of set up like, hey, what the hell is this thing even doing? Part 3 is like, hey, from part 1 we kind of got an answer. Part 3 is like, we're going to use trigonometry to get an exact answer, not using any differentiation at all. Kind of that 3-point method. But hell yeah, so let's dive in. So we have this thing spinning, and it's spinning around in a circle. Now, for the problem statement, it's going hella fast. It's doing this 17 times a second, at 1,000 revolutions per minute. What we're going to say is, because I had to break this problem up, you see these green lines? Well, these are when this is at 0, right at the top. When this thing rotates 45, hell yeah, we get to another green arrow. We're going to rotate another 45, booyah, we get to another green arrow. Another 45 degrees, hey, we get to another green arrow. 45, and then even on the way back, that was the other part of this problem. Being able to set it up like this, you can be like, whoa, okay, so it actually hits the same points going up as it does going down. Okay, sweet. So that's kind of the first thing. Now, mentally, what we're going to do is we're going to pretend that we're going to change the speed on this. We're going to say this thing is going 45 degrees per second. So whatever, that's the speed. It's going 45 degrees a second. So the actuator is going to be at the top. In 1 second, it's going to get to here. Another second, it's going to get to here, to here, to here. So what I'm going to do, this is kind of a cool thing to do, is we can set a stopwatch, and I can just I'm just going to move to here at each second. So here we go. I need to get into the rhythm, so we got to go faster there. 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we go slower, faster, medium, fast, medium, slow. Okay, hell yeah, so I think you get that. But this kind of just shows, okay, so this actuator is going different speeds. The other thing to notice with these rotational problems, and this one's kind of hard, but hey, when the actuator gets close to its top, well, here's one thing. The actuator is going to go up, and then it's going to start to go back down. And I'm going to say when it goes up to the top, it stops. And this is I like this, because this is Newtonian physics. Newtonian physics says you need to have a continuity. Something can't just superposition itself from like, hey, I'm going up, but now I'm just going down. You know what I mean? So if we throw a baseball up in the air, it slows down, it comes to a stop. At some point it has 0 velocity and then starts to come back down. So there's a lot of physics problems where that's useful. Anytime you have a change in direction, hey, that baseball got thrown up and then all of a sudden it's coming back down. Well, there's no other answer than at some point that baseball came to a stop. Now in quantum, realm, maybe that's not true. Maybe you could go from upward speed to instantaneously going with downward speed, but not in Newtonian mechanics. So that's kind of useful. So at the top of this, hey, it comes to a stop, and then as this actuator goes down, then it starts to go back up. So at the bottom of this, that actuator came to a stop. Okay, so now I'm going to go over what I kind of need to actually use these measurements to tell you about. Because this is kind of the second take of this video. Acceleration is always kind of bizarre, and it's always bizarre that you're going to find the highest amount of acceleration when you're kind of in these stop locations. So let's take a look at this. And so again, the distance between these green points is going to be 1 second. And on the way up, we're going to hit this green point, and then we're going to hit the top, come to a stop, and then we're going to come back down and hit this green point. So from going up to here, that's going to be 2 seconds. And now let's talk about what the definition of acceleration is. Definitionally, it's change in velocity, change in time. And but if you have a velocity that's going up and then a velocity that's going down, the change in that velocity, those two are going to add together. compared to, look at here. So like from here, here's my velocity. It's my change in distance. And then we know that's going to be 1 second. So this is a visual representation. That's why like a velocity vector. If I did an arrow right here, this would be a like a representative of the magnitude of the velocity from here to here. And then you can see that the velocity increases from here to there. Your average velocity looks bigger. Average velocity here is that small. So the change in the velocity would be representative of just the change in the distance that we see here. So we have that distance minus this. Well, maybe we get like maybe that distance. So then when we go back up to, so keep that in mind, because it looks like, how do we find the change in velocity around this top point? Well, we're going to have a velocity coming in that's that magnitude and a velocity that's going out at that magnitude. But because they're in opposite directions, when we take the difference between them, they're additive. So we're actually going to have that much change in velocity over that time frame. So let's compare it. So that looks like a bigger number for change in velocity compared to this minus this. This minus this is like that. So the acceleration from here to there is going to be less than the acceleration from prior to getting to the top to after to getting to the top. Okay, and then there's just one more thing to kind of clarify with these problems that comes up all the time. When you're just starting out, when you're just taking points and finding... So yeah, let's talk about the actuator before getting to the top, at the top, and then after the top. So before getting to the top, we're going to try to find the average velocity upward. That's going to be this distance divided by a second, let's say. Cool, and it's going to be going upward. But what we know is that the velocity at the top is 0. Okay, so keep that in mind. Because if the velocity at the top is 0, but the average is this, some number, this has to be twice. That comes up a lot in, and hopefully we're taking a small enough sample where like from here to there is a linear change in velocity. You know what I mean? And if it's not, then just make a smaller chunk. You would go from like, here to there. Okay, hell yeah. I guess the take-home point, though, is the average velocity doesn't happen a second prior. It doesn't happen the second at 0 seconds. The average velocity is in between. So at some point in between, we're calling that the average velocity. So if this is 0 and this is, twice, you're going to get to that average about halfway. Okay, so keep that in mind. Now we're going to come over here. So we know our velocity is 0, but, put that aside. We're going to try to find the average velocity. That's going to be this distance divided by 1 second. That's going to be the average velocity in between these 2 points. But we know this point's 0, and so this point has to be 2 as long as there's a linear relationship. And we should know it's linear because we're just kind of taking a small change in angle. Actually, 45 degrees is a hella change in angle, so it's probably not going to be linear, but we're just kind of keeping that in mind for this idea. So the average velocity will happen at like 0.5 seconds. So negative 0.5 seconds to 0.5 seconds. So if we take the change in the velocities, we find the change in velocities, and then we divide it by that same time period of 1 second. And so I guess I didn't even explain what I was talking about, but when you take velocity, you're going to take change in position divided by the time period from there to there. You're going to get an average velocity. But you need another average velocity on the other side. But now, where are those average velocities? Is it at negative 1 second? Is it at 0 second? Is this one at positive 1 second? Or is that at 0 second? So it's going to be halfway in between. And because they're halfway in between, the distance between those two velocities are going to be that same 1 second interval. Definitionally, acceleration is change in velocity, but divided by the time interval that it took to do that. So we're just doing that 1 second interval. All right, so hell yeah. So that kind of explains it. And obviously, on paper, our interval, this thing isn't going 45 degrees a second. It's going hella fast. So that change in time is going to be real small. And so if we do notice a change in velocities, we divide by that change in time, and that really increases that acceleration number. But hell yeah, this is just kind of getting a feel for it. And then at the midpoint, sure, it's going hella fast. Like, look at this. It's going really fast, but the acceleration's not changing. So it kind of hits this peak velocity that it kind of maintains for a while and then starts to slow down. Okay, hell yeah. And I guess the only other point was, look at down here. We have a change in velocity here in that direction. It's small. And then we're going to have a change in velocity from here to there, and it's small. So this acceleration change is actually pretty small. So like, hey, look at this. If we double this distance, like that is not even, that would be, doubling this distance would be a visual representative of the acceleration at this low point. But look at here, even like kind of right in the middle between 45 and 90, we're getting an acceleration that's just the difference between these two. So, and that's bigger than the acceleration down here. So that's where, you know, the last video is just like, sure, you can have a high peak of acceleration around point A. So this is point A to that point 0. And sure, you're still going to have a smaller peak here, but yeah, you might go down, but then for the most of this, you might stay up real high. So for maybe more than 90 degrees of the sweep, your acceleration is way higher than this other peak. This will be a peak, you know, as you then go back up to that point, and then the process is a full cycle. Okay, hell yeah. But this will be really cool to actually derive the equation and then notice those things. And even this is kind of a preliminary guess. Acceleration is a lot harder to see than just visually, like the velocity changes. Okay, so that's going to be part 2. And part 3 is going to be actually using trigonometry to do the 3-point method, but just a lot tighter. A very tiny change in angle, a very tiny change in time, and then we can figure out the velocity of that follower. All right, hell yeah.